this is the discussion I had with two humans I have deep into my heart, which are Olivier Terrien, which is my graphics programmer mentors, whatever. A human have a lot of respect for his knowledge and the way he approaches problem, and also Peter Shirley. So, welcome to On Decompile. This is the discussion with Olivier Terrien and Peter Shirley.
Our special guest, Peter Shirley.
Hey, this is Peter Shirley in Utah. Welcome to On Decompile.
Just introduce yourself one after the other. Peter, you could start, so people are gonna have a bit more if they don't know you.
Hi, I'm Pete Shirley. It's a pleasure to be here. I work at NVIDIA. I've been in computer science for 25, 30 years, something like that. And I've kind of had an obsession with ray tracing, thus I end up on your show. It's been it and C++ are the two constants in my life, and one of those is a good thing.
And Olivier?
Hi, I'm Olivier Terrien. I'm a graphics programmer at Cédrin. So I do mostly shaders and Unity, and I have a big interest in global illumination, so I think it will be very interesting to talk tonight.
And I'm Antoine. I also work at we are at the same job, Olivier and me, so Olivier and I. So I work as a graphic programmer too at Cédrin, mostly on shaders, and I think I'm all around graphics. I haven't come to a state in my career where I'm like, oh, I prefer to do real time, or I prefer rasterization I like to touch all the algorithms, and it's a field that keeps me up at night every time. So, and I also do the show that you're listening right now. So let's start with a very simple question. When was the first time you heard about ray tracing, and what was the first mention of ray tracing ever in either technical papers or academia research?
Well, I think the first time I heard about it was in a physics class, because when people did lens design, if the set of lenses was too complicated, they would just do ray tracing by hand often on a sheet of paper to figure out where things focus. So that was an old technique there. That's the first time I saw it. My understanding is the first time it appeared in a graphics paper was by Appel in 1968, so way, way back. And I think what he said was even with thousands of rays, it was still blotchy. So thousands of rays like now is what you take in a pixel, so it just shows how much Moore's law is accelerated. After I saw that in a physics class, I found Turner Whitted's paper. So Turner Whitted did his paper like when I was in high school. Turner is a double E guy who had been doing research on sonar for the government. And that's where he first saw ray tracing, was tracing sound waves. So the physicists, when they had to do something in a complicated domain, be it sound or light or whatever, they would simply trace the rays. Turner brought that into the form we know today. Like I would say approximately half of the intellectual mass of ray tracing is all in that one paper. It's really a remarkable paper. And there is a mistake in the paper, which I will leave as a quiz for the audience. Just send on Twitter if you can find it.
You did that too in your lectures on at SIGGRAPH in real time. You said there's an error in the paper, if ever.
Still a quiz.
Yeah. So the Whitted Turner was in what year?
He wrote that paper in '79, and he wrote the program in C, and it really had largely the structure we do today. It had adaptive anti-aliasing in it for pixel, like little quad trees, basically. It had a bounding volume hierarchy. I mean, it's really an amazing paper. And then he moved on and did other things. Turner has done many, many other things. And so ray tracing was just one of the villages he visited on his rampage through the research area.
And you meant now he worked a lot at NVIDIA, so...
Yeah, he and I actually overlapped as employees, much to my delight, and he's just everything you would hope he would be. And he was writing font rendering code when I was there for a VR device. I mean, he's hardcore, and he's still extremely creative. So he has a lot of ideas that are against the flow of current research, just like he did back then. I kind of think he's right. So one of his big things while I was at NVIDIA was there will be screens everywhere. And the moment the number of screens greatly outnumbers the number of humans, everything changes. And that's what he was really looking at is rather than attach the device to your head, just have screens everywhere.
Would you think that ray tracing is like an anarchist or finger to the system idea based on this this explanation? Like you went that G Turner with it was really against the flow. Was it like a controversial at the time?
Well, it wasn't controversial so much as it was viewed as an academic, esoteric exercise. And I think what that boils down to is it was slow. So you could kind of just look at Moore's law and see that it would be 20 years, 30 years before you could use it in a movie. And a lot of people who are, say you're 50 years old, that's kind of too long. And so I think there was just a lot of resistance to waiting that long. But I don't think anyone thought that it was a bad idea. It was thought to be an impractical idea.
Because not enough power, right? So
Not enough power.
and when have you? Oh no, go. Sorry, go.
I just think that Moore's law predicted, I think I heard Kajia first argue in the late 80s that Moore's law implied that ray tracing had to win. And that was when I was in graduate school and I would go to SIGGRAPH and go to these courses, which are excellent. And I found his arguments convincing. That was kind of what swung me over to thinking ray tracing was the way. I also found Monte Carlo methods very appealing.
Did Monte Carlo method games? When did it came in the story? So like right now we're like beginning of 1980 or
1984 in Cook's paper is when it really entered the picture.
and the
So,
Terence Cook. That's another flavor of ray tracing.
Well, that is a material model.
Oh.
So Torrance was a heat transfer guy at Cornell that did one of the first BRDF papers with Cook. Same Cook, but different paper was the 1984 Pixar paper that used random numbers to make motion blur and soft shadows is really what he did. And so if you've seen these pool ball pictures of some motion blurred pool balls, those were in 1984. And it was by far the most amazing image I had seen at that point. It was like someone sent an image from the future back into time. And then I was kind of sold. So it's not that I think people were more interested in real-time graphics at that point, and ray tracing was very much not real-time. So it wasn't really against the system so much as too slow.
And what was the so main research? The real time was like rasterization and stuff where we started to reach at this point. Did you see some, like, everyone was like, was there like two ways of seeing it? Like people real like you believing in ray tracing and doing like, this is the future, while some other were like, no way, that's never gonna work. Rasterization will change the world forever. Or what was your point of view at this time?
I don't think it was quite that stark, because in that time, Silicon Graphics had put out the first, like, really, I think, excellent, affordable, and when I say affordable, I mean $20,000. So for the price of a car, rather than the price of an aircraft carrier, you could get interactive graphics. And so you could sit down at an SGI terminal and with a Z-buffer, write something that would allow you to move things around interactively. It was stunning. And so I think it was really more a matter of aesthetics. If you have this A-B choice of, I can have really great graphics that run overnight, or pretty good graphics that actually respond to my input. It's almost like a personality test, which one you go for. It's like a wine or beer sort of question. They're both great. And the beer was more appealing to most people.
But the wine made it to time better. No, I don't know. I cannot
It
say.
got better with age. How about
Yeah.
that? Unlike beer.
And do you see that? So you clearly made the choice of ray tracing and focusing on this technique. When you saw this, you mentioned an image from the future. When you saw those pool balls, and we're gonna link that in the description. When you saw this, what was your like? How old? Or like, no, it's an impersonate question. But like, how did you felt? Were you like, oh my god? Like nowadays, seeing motion blurs on things moving is like,
Oh no, it was shocking. It was, I want to do that. So it was an entirely emotional decision. It wasn't really technical. It was probably poor career management at the time, but I was your age. You don't make good career decisions at your age, right?
yeah, that's. I mean,
The good news is there's lots of margin for error, so it doesn't matter that you don't.
And did you wrote ray tracer back then? Just
Yeah, I had to do an undergraduate thesis in when was that? 1985, and I did it on ray tracing as a physics undergraduate thesis. I had a very tolerant advisor, thankfully, because it wasn't really physics. It was more a pivot into computer science, and I wrote it in Pascal on a Mac with a 2-bit screen, and I was so naive about programming that I had 2 spheres and a checkerboard, and there was a different intersection routine for each sphere because they had different centers. So it was very unsophisticated, remarkably so.
And how long was it to generate? Like, because nowadays,
12 to 24 hours, basically.
for 2 sphere in the floor with a checkerboard.
It was Mac Pascal written by a chump.
Yeah,
So-
but still 24 hours. Oh my god, we're having it so easy nowadays. It's crazy. Ali, do you have?
I don't know that I'd go for that. I would say that the hardware is significantly better, like unbelievable. You can devote more computational resources to a pixel than I could to a screen. But the programming environment, I would argue, is worse than it was then. And it's mainly because the hardware is so complicated that there's just a lot of overhead in taking advantage of all the performance of the hardware. So the ability to abstract is not as large now as it was then. And it's a good thing, or we would not have interactive programs. But just the amount of pain in getting something to work, I would say, has gone up a factor of 10 at least since then.
And you mentioned the original paper had BVH in it, which I didn't know.
But hand constructed.
Okay, so it was. So could you just because BVH is like it's could you explain a little bit what it is for listeners that? So we wanted not to go too technical, but still like BVH in a nutshell.
Yeah, you could argue that most of computer graphics is judiciously turning order n algorithms into order log n algorithms, but it's very bad for your program when you do that. So you do it very selectively. And in ray tracing, you sent one or more rays, which is just a line from the eye out into the environment to see what you see in a given direction per pixel. And then each of those rays has to intersect or say, hey, do I hit you, to every object in the scene. And so the amount of time is proportional to the number of pixels times number of objects. And a BVH is a divide and conquer strategy, which is one of the only basic algorithms really in computer science, which is if you're trying to search for something, first divide it in half and look at one half and try and find it. If you can do that judiciously by saying, I know it's not over there, then you can repeatedly divide the problem into half. And that's what a bounding volume hierarchy does. It takes groups of objects and surrounds them, approximates them with one object, and then takes those groups, etc. I'm not sure if there's a good analogy in just normal life. Maybe you guys know one. What's a divide and conquer strategy in
I don't know, maybe going to the groceries, I would say like you go to grocery store and everything is mixed up and you just...
And if you know you want vegetables, you go to the edge of the store and you skip the middle.
Yeah,
So
something ish.
no. That's a classic search problem. You go into a store for a bottle of Coke, and you're going to be able to quickly, because of the way the store has been organized, narrow it down much more easily than looking on every aisle. It's very similar, actually.
And so we okay, BVH, I was just curious to have you. Maybe this cut is gonna be included. So just to make sure that the listeners understand, this discussion we have in here is going to be, there's going to be 2 episodes. There's going to be the whole discussion we have, but also like the story in a more like narrative way. So, and you mentioned earlier materials, and those are big parts of how rays interact with object. At the time, in like 1984-ish or mid 1980s, what were the state of the art like materials and ray tracing? Those two fields, were they talking together? Or so like you had the blend Fong and stuff, and eventually Cook Terrence went on, and but what was the way those two like domain of CGI were linked?
The way they got linked is people had been studying material scattering for things like satellite cooling. So real hardcore engineering problems. And that's where that Ken Torrance guy comes in, is that was his area of study. And they needed not only realistically scattering materials, but they needed them to be physically accurate. So if they built a satellite, it wouldn't melt. That's the reason they were looking at this stuff, is when the sun hits the satellite, how do they keep the temperature down? So they had to look at how the light would reflect between a solar panel and the body of the satellite if it bounced around too much in here. So they had to do global illumination.
That is so cool. So the Cook...
And
oh, sorry, I was just...
So my understanding is that Blinn and Fong had kind of developed this stuff on their own in computer graphics. And then Rob Cook was a student at Cornell, and he looked at that stuff and said, I should talk to some hardcore engineers about this. There's some in the next building. And he went and he found that Ken Torrance fellow, and they had a conversation, and that led to a paper. And then Torrance was kind of one foot in graphics for the rest of his career.
My God, I didn't knew that it comes from a, and it was like 1980. What year was it when the Cook Terrance model got officially introduced? 1982.
Yeah, that sounds right.
Okay.
Yeah, early 80s. Before my time, because I know I read it as an undergrad. So.
But still, it was around. And you, so maybe early, do you have a question? I know I'm a bit more talkative than you, but if you want to join, feel free. If you have an...
Maybe a more general question. Are you surprised that the graphics evolved the way it did? Like maybe regarding rasterization, ray tracing, voxels, triangles?
Well, I think, there's several big predictions I would have made confidently that have turned out to be totally wrong. One would be that everything is a small triangle. Like, this is shocking to me still to this day, because the big development that everyone knows was going to happen is that the gap between memory and processing keeps growing. So processing just more aggressively improves than memory access and networking do. So you would think that making a model into a gigantically tessellated, massive thing that's as big as it could possibly be would not be what would happen. You'd expect like NURBS to be everywhere, some higher order surfaces, and that absolutely has not happened. Like, finely tessellated scenes are the constant between rasterization and ray tracing. This is kind of amazing.
And why processors are not made to have faster bandwidth and memory access? Why are they more compute oriented?
Oh, well, I think this is just a matter of what's the natural progression of the speeds of processing and memory. But this is just what the hardware people say. I just take it as a religious fact that the saints have said. I actually have no idea why that is true. My knee-jerk guess would be networking tends to be 1D and processing tends to be 2D when we lay it out. But I haven't the slightest idea is the real answer. I'm sure some of the people in the comments can educate me there.
And do you think there was missed opportunities maybe in graphics, things that have not been explored yet or too late?
Almost for sure, because I rejoined NVIDIA 5 years ago, and rendering is a pretty mature field. So I was not expecting any huge improvements. And then suddenly, we get some crazy improvements in sampling that I did not anticipate out of people like Chris Wyman and Benedict Bitterly, that are really fundamental theoretical advances. And then we get AI coming in to do the denoising. So, probably the most insulted and disparaged area of computer science during my career has been neural networks. You really had to have a thick skin to work in that. You would be insulted, disparaged. You couldn't get your papers in. And now it's just completely taken over the field. And so if you told me people would be doing ray tracing with strange sampling algorithms, low sampling density, and then that would all be cleaned up by an AI program, I would have been shocked. And that's all happened in like 5 years. So I would assume a lot more is going to be coming. My guess would be geometric primitives in the modeling pipeline will change. But that'll take a long time, right? To change an art pipeline is non-trivial. And that's one of the reasons the triangle has survived so well, right? Is the art pipelines supporting that are fabulous. And artists know how to use them and produce amazing things. And so if we can get pictures out of that, we do it.
And let's, okay, I was sure it's going to go this direction. I was like, oh, let's make it just talk about history. And then we're like, we're three graphics nerd talking about graphics. And it was sure that was going to go all over the place. But, it's cool. That's the podcast. No rules, no things. The only rules is there's no rules. So I was wondering, because, okay, now let's get back a bit to the history side. And we could talk about AI later. And make even, maybe we could invite Vai, which is an AI researcher in here we have, and we could discuss with you. Like, everything is possible with this podcast. 1984-ish, there was this incredible representation called how actually lights behave in a scene, proposed by Kaguya, which is the rendering equations. And I think...
It's 1986.
1986, the rendering...
And the reason I'm so certain of these years is I started going to SIGGRAPH in 1985. Many people think 84 was the best SIGGRAPH ever. Looking through the proceedings, I kind of agree. So, yeah, you could argue correlationally, I really hurt the field by entering it. And then 86 had that very exciting paper to me. And that kind of changed the direction I went in grad school. And so that timeline's etched in my brain.
When you saw that lecture at SIGGRAPH, which I tried to find online, but it doesn't seem it's recorded. Maybe a VHS somewhere in the States have it. But what was because it's a bit of what the fuck. Like, this equation is like, what was your feeling? Were you like, the concept is quite simple, but it's like, so what was wait, let me rephrase. How have you seen this rendering equation in 1986 being presented at SIGGRAPH being like a game changer in the field?
Well, I don't think I saw the equation so much as a game changer, although it was. I didn't recognize it at the time. It was the diffuse interreflections. So I'm much more of a make the picture look pretty kind of person. And so I was concerned with what are the visual effects that are missing. And if you look at Cook's paper, the big visual effect that's missing is bounce light. So just diffuse interactions. And Kaguya gave a way to do that. And at that point, it was like, okay, everything is here. Now it's just a matter of cleaning up the details. And that indeed turned out to be true, I think. Because that same basic algorithm is still what everyone is using.
And the concept of the rendering equation is awesome. But still, from this 24 hours to generate two sphere in a checkerboard floor you had, was there a hype in the industry or like practical approach, or it was just like, oh, here's another paper, like?
No, it's very hyped up. SIGGRAPH always had a lot of hype associated with it. And there are many reasons for that. I think one of the big reasons is computer scientists don't really consider graphics to be part of computer science. And the scientific computing people don't really consider graphics to be part of computer science. And so it's its own weird little Switzerland in Europe, and or Quebec. And so graphics has always had kind of a chip on its shoulder. And so and it wasn't getting a lot of resources. I mean, that is why, even though it was a very important area, there wasn't a lot of funding going to it in any country. And so in order to generate just an industry, I think everything was more hyped up. Add to that movies and games. At that time, more movies than games just was a natural way to try and hype things. A further thing is, because graphics wanted to be taken very seriously, there was a tendency to show off with kind of muscular demonstrations of math prowess. I mean, I kind of think of it like these car shows with big engines on their cars. That's kind of how papers often were. And
Like putting integrals everywhere, or
yeah, like putting integrals everywhere. And sometimes that's just needed. Like, oh, I need to sample this light source. How do I formalize that so that it comes out right? You have to write down a bunch of integrals. But often it's just muscle flexing. And so there was often a lot of mathematical hype. And that, I think, is why the paper, although it was very influential for me, I didn't quite see how important it was at the time, because most math in graphics is unnecessary. And so you see a bunch of math, my first reaction is, this paper probably is not useful. And this is like trying to hide the fact that there isn't an important idea here. Exactly the opposite was true in that paper. So I did find it exciting, but not as exciting as I should have. And I think the real insight into that paper was that you can formulate this light transport problem as the light at this point is just an integral over the light at every other point, and it's recursive. And this makes intuitive physical sense. But by the way, that same integral does appear in Immel's paper in that same proceedings.
What paper? Sorry?
Immel, Immel. It's a radiosity paper that solves the same integral equation. And for some reason, it just doesn't get as much love as Kajia's paper. They're both great papers. The Immel paper also has that Torrance fellow we were talking about earlier on it. And they're right next to each other in the proceedings. And I think Kajia gave just a much more clear explanation. That paper is extremely clear at some level. So none of the math in Kajia's paper is gratuitous. It's really super clean.
And then we're in 1986, 86, sorry. And the movies starts to, like, there's definitely more ideas and stuff. And people are like, oh, maybe we're going to have, like, computers are getting better and better, slowly but surely. When do you, in your life, saw a movie, an image, a TV show, or like not like the result of a paper, but like really like a commercial on TV or whatever, something you saw on TV, it was like, oh my God, okay, ray tracing is getting over there. It could be just a little effects, you know.
Oh, I think Monster House, the movie out of Sony.
Yeah, that was
the first movie that was made with Arnold, and just diffuse interreflections were everywhere there, and that really caught my eye.
But that was 2006, so there's nothing that intercept your highs in those 20 years, or?
Oh, that's a good question. I mean, certainly there were tons of academic images that did this. Let me think. This is a hard one. I have to resort things in my brain.
But that could be an academic research too. Like, what was an image that you saw and oh, that's next level?
I would say some of Henrik Jensen's photon mapping images were super amazing. Photon mapping on gases, clouds, milk, stuff like that. That was something Henrik figured out how to do. The really important thing that he did there is there was a old thing about tracing light rays from the eye to paint things like caustics, like the patterns you get when you put a wine glass down on a table and you get the candle going through it. There was lots of work that did that sort of thing based on backward ray tracing from the eye, but it's all very awkward because you had to put a texture map on the surface and log where the light went. And Henrik really had the insight to separate the data structure of those photons from the geometry itself. That's what made it practical. And really, that basic algorithm is what's used in every movie still to get a caustic.
And it was like from what I see, photon mapping. So maybe we could go like, what is, because it seems like photon mapping from after the Kaguya style-ish kind of, would you define photon mapping as like the next like logical event in like all these, like I want to say offline rendering-ish, because photon mapping is not purely ray tracing, but like let's stay in the cinema/offline rendering.
I wouldn't say that it was the next logical step, because looking back on that era, it was, and not just in computer graphics, but in programming languages and operating systems, it was just a brute force search of the entire design space. There were enough people working on enough things, and we were all dumb enough that every idea was tried. Some of them worked. So I really don't think anyone they were all very confident in their predictions. And I think the things that worked, their proponents' predictions were correct. I really think that's more coincidence than anything. We tried everything you could think of about how to move light around, and you would find out the hard way what worked and what didn't. And I think that's the era in which I became a very hardcore empiricist. See if it works, because your ability to predict whether it works is relatively poor.
What was your most exotic computation to move light around? Ideas or algorithms or weird idea you had to move light around?
That's a good question. I'm really more of a KISS person, so keep it simple algorithm person. So, did I have any like wild ideas? I think the only really wild idea I had was allocate a budget of 1 million rays per pixel. That's what you should aim toward, is the ultimate place you expect to be. So ironically, now we're at 1 ray per pixel. The number of rays per pixel has gone down. So that was like I'd say my biggest error was super brute force Monte Carlo. Get rid of stratification. Just assume you can go aggressively in parallel. So if you could use 1 workstation per pixel, just go for it. And you could easily do that now, but I don't think there are a lot of applications for that except physical simulation for actual realistic design.
Still in movies today, sometimes rendering a frame takes, 12 hours or something. It's crazy how much.
Yeah, the number of hours per frame has gone up over time. But it probably is leveled at 12, because you need to be able to do it overnight to look at the shot in the morning. Sometimes they go more, but I think the design process in film, from what I've heard, is that you really need to be able to see the frame in the morning.
Yeah. And 12 hours for one image? It's crazy. When we it's crazy image, but it just fascinates me from what you explained as that nowadays we can render New York City and almost feel like it's a real picture in 12 hours. And in just like 25 or something years, let's get back to this idea of the sphere. 2 sphere and a checkerboard, 12 hours, 25 years later, New York City in ish PBR, really like physically accurate.
Though I do wonder, if you look at some recent work out of the AI group at NVIDIA, you take a rendering from Minecraft, incredibly crude, and you just take an AI program and make it photographic. It's not perfect, but it's shocking how well it does. when you look at how good game graphics are, I really wonder, do you have to get any better than that? Is the last mile just done by AI rather than by doing it overnight? Because the difference between the visual quality of a video game frame and a super hardcore film frame is not that high. And so why does it take a factor of 1,000 more effort to get a little bit diminishing return of some kind, right?
Do you think there's the diminishing returns maybe in the movie industry? We sometimes see things at SIGGRAPH where a very complex algorithm only improve marginally the noise in the image. So is it like too small of an improvement?
Well, it can really be critical in making it look better too. Maybe it gets you out of the uncanny valley, right? And so
Yeah.
I would say we don't know is the real answer. And also, AI has been great at taking problems that are solved poorly and make them solved well. But AI has its own last mile problem, right? And it's really hard to just push the envelope of how good it is. Like you can see the results at the AI conferences kind of leveling off a little bit. The fact that they're the best algorithm out there, that's here to stay. But that doesn't mean we can expect their improvement to keep rolling the way they have been.
Do you think that we could just have an AI post effect that would do the small detail that are missing right now in graphics?
I would be shocked if that doesn't work in at least some contexts. But it's my intuition is poor. Like AI's worked so much better than I have expected it to the last 5 years that the one thing I've learned from that is my own intuition is probably not that interesting.
And we mentioned AI a lot. Seems like the new thing. Let's get back a little bit back in time once again. Sorry guys to be I'm like we're discussing and stuff. It's super like we should make this show could last 3 hours. I mean, honestly, there's many ways I'd like to go. But like we talk about GI, Kajia, like photon mapping that was like from 1995, the year I was born, to 2001. And then after comes this I don't want to, like Cars, the movie Cars. There's this idea that it was all ray traced movie, and we had Inigo Quilez, which worked at Pixar back in the days, that told us that it was not that much all path traced. It was very the first Pixar movie that was really purely path traced was Monster House. No, not Monster House. What's the name? Monsters
Inc. I didn't
Yeah.
realize that was path traced.
But the newest one, the University Monster. Anyways, the newest one. But I want to go a bit back in the time, early 2000, 2004, 2005. The video games industry is reaching to new levels. We're starting to see GameCube, Nintendo, PlayStation 2, the first Xbox. Then also there's movie like Cars. We're like, oh, this is stunning graphics. There's a buffer of time where we could talk about Toy Story, which had its own story. We could go on on that. But like, where were you at this time, and did you felt like, oh, rasterization is taking over the world with all these gaming? But on the other hand, there's also movies that were getting incredibly well, beautiful. They were getting more. Can we say beautifuler? No, they were getting more beautiful, nicer.
Well, I was in academics at the time, so I had the luxury to just wait out Moore's law. Like, I don't think it was a very complicated mental equation that computing is doubling every 1 to 2 years in speed. The number of pixels is not going up that much, though ironically, it's really jumped lately. So, you can kind of plot it out. Sometime around now, it should be very practical. It's a simpler program, so there's fewer interacting hacks. I think there was a software engineering argument. So I had the luxury of just sitting around and waiting, as did several other people in academics. But if you had to make a movie, it didn't matter that you thought in 5 years it was going to be fast. I'd say, though, a big surprise to me is video games have adopted ray tracing much faster than I expected. And I think that is a cultural thing. So the movie industry was very slow to adopt ray tracing and was very resistant to changing their tools. The video game industry, it was almost like they were bored. They were so anxious to adopt new tools. And I was almost like, hey, slow down. Are you sure you want to do this? So the video game industry seems to have a culture of people that are used to constantly changing software and hardware environments. And so they're just, I think it's pre-selected for a type of person that is more change tolerant. And, oh, this is cool new tech. I want to learn how to use it. And probably that goes back to like the shading hardware that came out. It was very programmable. That was an exciting new thing. And the game people were all over it. And again, they've just been all over it. I've seen very little resistance to fundamentally changing the core pipelines, even though the pain that is going to be endured by that is the programmers at game companies. So maybe it's the game companies are full of masochists. That's possible.
But why is the movie so conservative, you think, regarding rendering tech?
Well, I think they have a very established pipeline that really works well enough and has an artistic flow. So like the jump in realism from the raster hacks were so good in the movie industry that it wasn't that big an improvement to get ray tracing. I think
what were some of the most like incredible rasterization hacks?
Well, I think one thing is you can place a ton of point lights by hand to create artificial global illumination. So if you want to bounce light on your cheek, from the wall, you just put some point lights in by hand, and they had really incredible shading artists. And so the hacks were not just technical; they were artistic. Though there was an interesting thing from that Monster House movie. The Sony people said that when they switched from normal illumination to global illumination, the number of lights per scene halved. And so you literally had the shading job just get much easier because not only were there fewer lights to place, you didn't have to monkey with them as much. So the artists immediately liked the bounce lighting. And then I think once you get the artists on side, you're on a roll. I think another thing that changed it is the Pixar algorithm, the Reyes algorithm with the micropolygons was just so awesome and worked so well that it created a real barrier to entry for anything new. I think if that program hadn't been so amazing, it probably things would have happened sooner.
And what is the name of this Oh, sorry, Ali, if you wanted to go. I was just like, what's the name of this algorithm and how does it work? Just because I want to read more on that and narrate over.
Well, that was another 1984 paper, the description of that algorithm. It was called the Reyes algorithm, which stands for, it's like Point Reyes in California, but it stands for renders everything you ever saw. And
Reyes, Rayes?
Yep.
Okay.
And it's 1984 paper. It's a brilliant systems paper. Like anytime I think about designing a system, I go read that paper because they set up their constraints and they just figured out how to do it. And what that paper really gave us was a practical method to do displacement maps. And once you have displacement maps, you have incredible visual quality. And simultaneously...
I think they made the rendering in the texture space, right?
The rendering in texture space.
Like they rendered in the texture, they do the shading in the textures
yes.
instead of from the pixels.
Yeah, they dice the micropolygons down in texture space and then color them and then just project them on the screen. Super simple.
Why do you think we don't do that in games today?
It would work. It's actually a very good architecture. I'd say the only reason not to do it is shadow quality and specular reflection and bounce lights. But it's a fabulous way to do things, actually. And in the end, 50 years from now, maybe we'll do that again because it's lower power. Maybe power will end up telling the entire story. You want to be able to do all your games on your watch and then project it onto your wall. And just from a power standpoint, that might be the right play.
RenderMan removed the Reyes rendering in 2016. Just if you're
Yeah, see, that was some staying power. If you think about that, that was an algorithm that lived largely unchanged for 30 years. That's incredible, right? So that I think is a big part of the story. In some parallel universe where no one started Pixar, that the movie industry would have developed differently. But because they did something that works so incredibly well, it just took a long time for anything to modify it.
And what is the role of Pixar on the ray tracing industry or offline rendering industry in general?
Well, they really invented a lot of the core algorithms and then didn't use them, ironically, because they were too slow. They also did programmable shading first, I think. The old shade trees, Pat Hanrahan stuff, RenderMan shading language. I mean, really, you look at that, it's like a Los Alamos atom bomb kind of project. It's just incredible what they did. And Pixar is not published so much that you can't probably sit down and in a week read every one of their papers, and they're all worth reading. So, and I'm not just kissing ass there. I really do think like they didn't bother to write anything up unless it was very impressive. So that's why, and so they haven't done very much. You know, Pixar doesn't have tenure, so there's no reason to publish something that wasn't really critical.
So we're now reaching the point where Pixar changed a lot of the ray tracing world. Movies like Cars starting to say, we're all ray tracing, but not that much and stuff. And it brings us to this real-time ray tracing, which what was your first reaction, or how did you expect that one day there's going to be like real-time ray tracing hardware?
Yeah, I did, but I didn't expect it to take the path it took. I do remember the first real-time ray tracer I saw, which was Steve Parker at Utah, was a grad student then, did it on a SGI Origin. I think it was the 32 processor machine. I can't remember, but it was a very fancy machine. And Silicon Graphics had kind of a niche market there where they really networked workstations together super well. So you could write from 32 workstations onto one screen at 60 frames a second. I mean, no one else had that kind of tech. And Steve, is just a side project over Christmas, wrote this interactive ray tracer that just worked because he was just an extremely good programmer, very good at making things fast. And I walked in and saw it and said, oh, wow, that raster hack, how does that work? Like my brain couldn't process that I was seeing ray tracing. He's like, oh no, it's ray traced. I thought it was a prank at first. And that was when I appreciated, this is going to be big. Because when you see it interactively, it really is just fundamentally different. Now, it turns out that there were interactive ray tracers before that, particularly one by Mike Moose at when was that? The late 80s. Mike Moose is spelled M-U-S-S. He's the guy that wrote the internet tool Ping. So when you hear Ping, that's the guy. Fortunately, he died relatively young. But
yeah, we talked about that in the previous show we made.
Yeah, and so he did it first. Then, meanwhile, there were various people, particularly I think Engelwald and Alex Reshetov, just really hacking the PC to do ray tracing as fast as possible. So you could do it interactively on one PC. So it's kind of a convergence of various people just trying to do things very rapidly. And basically, at some point, the hardware got fast enough. Those people all made it happen a little earlier because they were just such gifted programmers.
And the future, what does it look like? Real-time, AI?
Well, I'd say the big question in computer science in general is what happens in your house and what happens on the cloud. And my kind of bias is everything will happen on the cloud. Almost no computing will be local, but could be wrong. But I kind of think Netflix tells us the story of what's going to happen in graphics in general, which was lots of people had like a high quality home theater in their house and Blu-ray, and they're watching it. And then Netflix comes along and says, we'll provide you something much lower quality, but very conveniently. And you can watch it on your laptop in your bedroom or on your little TV. And so everyone had the question, do I go load up the Blu-ray player and stick the Blu-ray in and get it on my TV and go sit on the couch? Or do I just watch something pretty good right where I'm sitting? And pretty much all of us did both.
This is
and
so
over time,
this is so much. I remember when I was in high school, I could not have a credit card because I was not 18, and I was telling my mom, I need Netflix, and then she was like, why do you need Netflix? We have a TV. And I was like, no, I just want to chill in my bed and watch Netflix. But
that's what happened.
And it's yeah, continue your idea. Sorry, I cut you.
And so basically the internet was not good enough for Netflix. I think in Canada in particular, there were all sorts of brownouts when Netflix was introduced.
Oh.
Because the network just was not up to the bandwidth. And so gradually Netflix put in servers near places to batch stuff, and the network got upgraded. And once it got upgraded good enough for most people to simultaneously watch something at 30 frames a second, then that was that. It was done. No one's getting a Blu-ray after that. And a key thing was latency doesn't matter for that application, right? If your movie's lagging 6 seconds and starts 6 seconds later, you don't care. So that it can buffer it up. And so the internet's good enough for that. And we are lucky that it is, because that's why the pandemic infrastructurally has gone as well as it was. I mean, who would have predicted that stuff would just work when everyone started working at the same time with this kind of conferencing? And the answer was, we kind of gave it a stress test by having everyone watch Game of Thrones. That was what made the internet what it is. And so games will have that happen if the latency of the internet can be brought down to manageable levels. And the latency on like a game console, from where you pull the trigger to when you see the action on the screen, is larger than most people think. So it's an achievable level. Our current internet is not there. So the question is, can we upgrade the entire internet a full generation everywhere? And eventually we will, right? And when that happens, I think then it will all be cloud gaming. And my argument for that is, if you want a really high quality gaming experience, ultimately you should have a PC, right? The graphics quality is just higher, but there's not enough large enough markets, so it's hard to put enough development time to really make that effective. So you have this whole multi-platform problem. You guys know this better than I do. Like, it's just hard to be a game developer now because of the plethora of platforms, right? So you have to make it work on the lowest common denominator. It's hard to do other things. So that's just an awkward environment for software developers. Further, it's awkward for a consumer. You have to buy 4 different game consoles because you want to play the exclusive titles. You have a PC, and then you have to be your own systems maintenance person, your own IT person for this PC. And so, for example, I can't get my Oculus Rift to play games off of my PC because, for whatever reason, when I go through the 13-step procedure for hooking up that cable to the Oculus Rift, doesn't work. Is it because the game doesn't work? Does the driver not work? Have I misfollowed an instruction? What's going on? It's just too awkward to try and be a consumer right now because the hardware is changing so fast and it's so complicated, and the OSs are OSs. So if you can just press go and get a cloud game to where someone else is doing all of the IT, and when new hardware comes along, you don't have to go buy it or decide whether to get a graphics card and install it. You just, keep your
subscribe.
Subscribe.
$20 instead of $10 to have the sexy rate. So honestly, so like from a human perspective, like not necessarily technical, but like, do you really think that from Olivier and I were around the same age. Do you really think we're gonna see this? So like no hardware in our house, just like do we?
That
we
would be
really-
the extreme view. I think that's certainly one thing that could happen, and it's what I would bet on personally.
In how long
But
would you think?
But another thing could be what comes to your house is like some Minecraft-like imagery over this internet, and then AI makes it photorealistic, and that AI hardware is in your house.
So that's the last step of the story, the AI part.
Yeah, that's one possible future.
Is-
And so I can say that at NVIDIA, what the basic NVIDIA strategy is assume any of these things are possible and make sure whichever one of them happens, we are really good in that ecosystem. And
Do you think that in the cloud, the computing power will stay roughly the same as one PC per person, let's say?
that is a really good question. And I think it's all a matter of the economics will determine that. So right now, like if you play a PC, we have some crazy light here. It is sunset here in Utah. I apologize. I only just noticed how strange the lighting is. If you look at the fundamental difference between gaming right now, where the consumer pays the power bill, right? So you plug in your 500-watt PC, you pay that bill, right? But in cloud gaming, the server company pays that bill. And so is the consumer going to want enough quality that they will be willing to pay more money? I think the answer is yes, because right now, if I want a 3090 in my desktop, I pay for that 24 hours a day, even if I only use it 2 hours a day. But if that 3090 is on the cloud, it can be split between 10 people, as long as their peak usage hours are different, which it's not, right?
Yeah, but right now the GPU price are extremely because of the microconductors penury. How do we say that? Penury is the shortage. Yeah, sorry. Like the price are. Sorry, I'm kind of making the black advocates in here, but it's like right now your GPU it costs so much. It's out of price. But I'm more like I love to have my hardware at home. I don't even have Spotify. I still have an MP3 player, and I put my music. So I'm like I don't know. Maybe it's me that just I love having my files. I love having my hardwares at home. Maybe it's just me, you know. Some people are like, oh, why do you still have a iPod? I'm like, I don't know. I love it. It's like it's not connected to the internet.
There will always be a phonograph industry, right?
Yeah.
So there will always be niche industries, but I think most people are very lazy about their hardware. I am. Like I really like the idea of someone else doing my IT rather than me doing my IT. But I also just the economics of it, I really do wonder about, because when I was your age, the big question is, how do I afford a car? And, you know, a PC is a much bigger part of a person's life now than a car is.
Depends for me. I don't even have a driving license. And I told my mom called me the other day and she was like, so when will you take your driving license? I'm say never. And she was like, why? And I told her, the day I'm going to have a car, it's going to be driving by itself and I won't give a crap about having a driving license. And she was laughing. I was like, I mean, I live in central Montreal, so I don't really need a car, but yeah.
No, that makes sense. And in urban environments, it makes sense now.
Costs a lot of money.
I would assume that that's something I'm actually willing to be more confident on than I am about graphics. Self-driving cars will be everywhere pretty soon. Now, pretty soon is a very vague thing. And that's also like a weird cultural issue in that I think self-driving cars are already better than humans, but they need to be like 500 times better than humans before we will culturally adopt them. Most of people your age I know are not learning to drive. So I think that alone is just a very telling phenomenon.
And a lot of people of my age and like younger generation, like let's say 18, 25, 20, whatever, something, like some people don't even have computers in their home. Everyone is on their cell phone. I'm like, yeah, I need a computer. Anyways, like that was so it kind of sorry, I'm just gonna land the plane. It's a bit I think I need to heat, like as I said, I'm back from like running, like from making 45 kilometers of bikes, and I was like, whoa, and it's already been 1 hour. Ali, do you have more questions? If you want to go, that would be nice, because I'm a bit, I think it's like, I'm a bit stressed, I don't know.
Maybe a question about ray tracing, but I don't know. Maybe it's a weird question. Why do you think we use ray tracing, and why there is no beam tracing or another form of tracing? I don't know, cone tracing, whatever.
So this is a really good question, and that's another paper, a Canadian paper, ray tracing with cones from 1984. Amazing paper, and I have wasted untold amounts of time trying to extend that paper, and so have a lot of other people, because it produces just incredibly beautiful images. Which is, instead of sending out a point to say what's seen in that direction, send out a little cone of what's seen in that little area, which handles all the anti-aliasing. If you make the cone wide on shadow rays, you get soft shadows. It's just a beautiful algorithm. Pictures look great. That turns out to be hard to do, just empirically. So people tried saying, let's approximate the cone with a set of rays that have a shared origin, say, and approximate a cone. Very attractive, because you can do it with SIMD. There's all sorts of computational advantages to this. And for whatever reason, it's had, to a first approximation, zero impact. And everyone I know has found this idea attractive. And it seems to be just to have some problem that's not well understood. Like, why doesn't it work better than it does? And the answer is no one knows. My suspicion is divergent rays turn out to be very useful. And coherent clusters of narrow rays turn out to not yield enough benefit relative to single rays. But that being said, this is like a super interesting area. And if you change the representation, so like have a sparse voxel octree or something, cones become very attractive. And maybe we're using the wrong representation. So I think that's something we're seeing right now for the first time in a long time, is people are reevaluating the representation of objects. Maybe it shouldn't be tiny triangles. And once the representation's different, these other non-simple rays become attractive. So people are really experimenting with voxels again, and they're really experimenting with sign distance functions again.
Yeah, I wanted to go on the SDF. What was like SDF and ray tracing? Do you see something there or not?
I do. It looks very attractive. And I do think that if you look at the first time people looked at this stuff in the 80s, 90s, and they all like died. You know, why did they die? And I think they usually died because of the last mile problem. Like, if you use voxels, it's very hard to get fine details. So what do you do when you get close to something? Well, maybe AI fixes that. And the last mile problem is handled by AI. Because the moment you have sign distance functions or voxels, the LOD problem gets a lot easier. And this this probably also is impacted by, is the metaverse hype, or is it something that's going to be real? Well, we have some giant shared graphics environment and VR helmets, some cyberpunk future, or won't we? And if we have some giant shared representation, then level of detail becomes super important. It's probably super important anyway, but that probably has to exist on the cloud, right? If you're going to have a giant shared environment. And again, I think you'll find a lot of different opinions. So the amount of actually the debate on VR and the metaverse reminds me of all of the debates in the 1980s. Will we all be doing functional programming 30 years from now? Was the kind of arguments you would have over beer.
So like Lisp would take over the
Lisp.
world. Yeah.
Yeah.
Was there a trend there, honestly, 30 years ago, where everyone was like, that's going to be the way to go?
Well, I would say there was a incredible progress in programming languages that was happening constantly up until maybe the mid 80s. And it was very unclear where things were going to go. But every couple of years, there was real improvements in the real operations of programming. So like C++ versus C, various object-oriented languages, the functional languages were getting cleaned up so you could compile them and they were fast. So there seemed to be a lot of progress. And then, boom, it just seemed to stop for 30 years. And now it's happening again, interestingly.
And what is your thoughts on Java? You're not forced to answer this question.
Well, I have a very narrow view, pardon me, of programming. It's like, how do I use it for graphics? And when I saw Java come along, I was very excited about it. So the first course I taught at Utah, I didn't know Java. I said, let's do it in Java. And I told the students, we will learn Java together. To my surprise, there was no rebellion. Like, people were very game. And we all learned Java together. And the lesson that came out was Java was awesome in that you can run it anywhere. And it was very well defined. So like the only time ever I was able to run automatic grading scripts, and regardless of what machine people developed it on, I could run it on my machine. This has never happened again since. The lack of operator overloading was just a showstopper for graphics programs, in my opinion. It was just so much more complicated looking. And then it was slow. It has appeared to remain slow. I also thought at the time that security being kind of built into the language from the get-go was just a good idea. That doesn't seem to have caught on. I think it's even a better idea now than it was then. But somehow secure languages have not caught on. So I kind of feel like we're in, I don't know, we're like the Greeks, ancient Greeks doing physics. We're onto something, but I really think stuff's going to look a lot different. I think that right now, programming has become very difficult. Like, it's just not a very attractive thing to do to someone who doesn't know how to do it. Because, oh, I have to install this driver. Oh, which version of this are you using, etc. I think Python is actually the thing that's going to change everything. Because it is the very first language that people are taught in school that is used by anyone in real life. That's never happened before. What's taught in school is always some language no one uses.
Python. I know everyone loves Python. I love it.
No. I think most people don't like Python, but they use it because it seems to produce better. Like, I don't actually like Python, but I use it all the time because
It's
if
everywhere.
I say, oh, it's not only everywhere, it's, I need something to render fonts. Oh, here's a package. I'll read the documentation, install it in 5 minutes, and 10 minutes later, I've rendered fonts into a raster image.
Yeah, that's the thing with Python. There's a freaking package for everything. Think about something. The other day I was like, oh, let's have I made a, anyways, MP3 generated like for DJ mixes, and I was like, oh, there's probably something that already exists where I could take a bunch of songs sorted by BPM and just made a mix.
Exactly.
5 minutes is done. It's like, oh, well, I wanted this to be a journey of audio programming, but it seemed like it was a journey of just one weekend.
I also wanted to graph something off of a data file I got off the internet. I was able to do this in Python in like a page of code. And I wouldn't even know how to approach it in C++, which is my language of choice. Because it's not, C++ is a language, it's not a development environment, right? And I think Python is that's not the first one, but it's, I think, probably the first one that's got wide adoption, where it really is an environment. There's some concept of user interface in the internet, and sound and video. So I think I think we're in an ugly teenage years of programming where it's just been getting more and more awkward, and now it's becoming an adult. And I think Python is going to be that adult.
What about Python and OpenGL, DirectX, or any? Have you seen? Because you've made your. I saw last month. I think you made a SIGGRAPH course about, and I watched it, and it was very nice. About, like, basically ray tracing in Python ish was.
Ish, yeah.
Ish, very
well,
ish.
I do think that Python's OpenGL bindings are really nice. Like, that's a really pleasant environment to write OpenGL code. But slow. It's slow. So Python is a really excellent way to interface to a good underlying toolkit, which is what AI is doing, right? 98% it seems of AI code is now Python, but the engines are obviously not written in Python. So I think we're seeing an era of programming at a higher level rather than low-level programming, which makes me a dinosaur. Like, this is not a very natural thing for me. So that I think there's going to be an interesting bifurcation of computer scientists into the people who write those engines and the people who use those engines. We've seen that in games for a long time, right? There's the people who write the game engine and then the people who use it. And they're pretty different types of people.
But still, we need both.
Absolutely. And so that's probably going to be the future.
Gee. Oh, sorry, I was switching to French. I was like saying, on manquera pas de job, meaning we won't miss any job. It's crazy. Ali, do you have another last question or something? We're already at 1 hour and almost a half, so I was like, if you have a question.
Maybe a last question. You mentioned graphics API. Do you like newer APIs like DirectX 12 and Vulkan, or do you
Well,
think
I gotta
they're too
say,
complex?
I don't like any graphics APIs. To be
Why?
honest. They don't usually make a lot of sense to me. Now, once I really dive in and use one a lot, then it's fine. I think that the shading languages that we have are like the greatest thing that's happened in graphics. Like, these are beautiful things, right? And writing a shader is super fun. Debugging it might not be, but writing it is. And I think I think it's that issue that has been coming up. There's a double-edged sword. By having such incredibly fast hardware that's works, you want to squeeze every last drop of blood out of it. And that means the programming interface to it's going to be complicated. And that just goes with the territory. And for like a banking software, you can go use Smalltalk and it will be fine because all that matters is that it works. And that matters a lot, right? But for real-time graphics programming, you really need to be able to get all of the performance. And that means you need hooks into the hardware that are pretty low level. At the same time, the hardware needs to be able to develop. And so this interface is very rough. And I think the only reason this is not like a flaming disaster is the API standards boards and the graphics companies have cooperated pretty well. Like, there's mutually assured destruction for the software and hardware people if you do this too badly, right? And so, like, DirectX ray tracing, I thought was pretty sweet design overall for like the first iteration of this. So I think as the algorithms change, we're going to go through an awkward period again. But if a standard exists and is widely adopted, I think is far more important than how good the standard is. And that's the Python thing. Like, I literally don't know anyone who actually likes Python. It's this weird kind of awkward language, like C++. It's this weird, gargoyle that somehow seems to work really well in practice, but I can't imagine anyone liking it. Like, do you know anyone that likes C++? We all use it, but do you like it?
Depends I think I like it. It depends. I like it for the sake of being effective, fast, and I mean, and now I'm saying that I'm like, and I was about to say all the libs that comes with it, like all the, like if you want to write OpenGL, no way you're gonna use anything else than C++.
Yeah, it's the effect
Yeah.
that you want.
So
So I'll make an alcohol-based analogy. It's like, 180 proof bootleg liquor moonshine. You don't like it, but it's very effective.
true.
And that's kind of what graphics APs are. They're, they burn your throat. They're problematic. They might make you go blind, but they get the job done. And I think as long as 60 frames per second is much better than 30 frames per second, all real-time APIs are going to be a little awkward. Just goes with the territory. Because there's a trade-off between cleanliness and effectiveness. Now, I'm not a programming languages person, so I don't actually know what the limits of these possibilities are. There are a bunch of people at NVIDIA that work on trying to make this stuff clean. And so, for example, before shading languages and after shading languages, I would say is a huge bifurcation in computer graphics. I imagine there's more stuff like that coming.
Wow. Very, very well expressed. Well, I think we're going to, like, having discussion about language is almost a philosophical topic. We could go on forever and say, oh. And I was like, oh, so let's wrap it up a little bit. Thanks, Olivier. Thanks, Peter, for joining. It was a real discussion that went a bit out of what I was but it was cool. I was like, so we talked about a story and then also having discussions all around so people could, so there's going to be two versions, the story version, which is going to be a much more documentary audio, and also the whole chat. So,
okay.
And Ali, if you want to add something in last, or Peter, or whatever, Peter, your book, Ray Tracing in One Weekend, Ray Tracing X, because I always write Ray Tracing X when talking about your books, because everyone is like, what is the Ray Tracing book you're mentioning? I'm like, it's the Ray Tracing series mostly. That's the way.
Well, I'll tell you a book that needs to be written is Kevin Suffern did a book called Ray Tracing from the Ground Up, and I don't know, the late 80s. Fabulous book. It really needs to be updated, or some version of it that's really a full, from the ground up, several 100-page ray tracing book. It's dying to be written by somebody. It's not going to be me.
Maybe, I don't know, maybe one day you will write, maybe we will write, who knows. But this is the book, I think, that Matt Farr says in his on his blog, from that he traded a few pizza for this book. Like, anyways, it was like, not traded, that's not a good term, but it was like saved money for this book instead of buying booze and pizza when he was in grad or undergrad school.
Awesome. That's a very good book. Yeah.
So, Ali, do you have a last subject you would like to end up, or I think we had a good chat.
Maybe a last question. Another weird question. Do you think that graphics card need to be deterministic, or could they be like just produce visuals that doesn't give the same result every time?
This is a very interesting question that I've actually never thought about, which is kind of an underlying theme of rendering has been Monte Carlo methods have dominated. And I expect that to be true in most of computer science. Over time, Monte Carlo algorithms will become more and more common. If that is true, then the hardware should directly support them and implement Monte Carlo algorithms themselves. That sounds like a fabulous PhD thesis to do, actually. Now, how would you do the random number generation? Would you have maybe you could take the incredible miniaturization of hardware to where the circuits are firing only probabilistically? Maybe you could make that an advantage. I'm really just speaking off the cuff here. I don't know. That sounds like a great idea, actually. And I do think that often Monte Carlo algorithms just work better. It's just a weird historical anomaly is most computer scientists don't like them. So just aesthetically, not for any technical reason. They engineers tend to like certainty, and Monte Carlo algorithms are only certain in their expected value, right?
Yeah, it must be harder to debug algorithm that can change every time.
Absolutely true. Yeah, that's absolutely true. And that is a non-trivial cost.
Yeah.
Incredible. Ali, maybe you could join the monthly discussion with Peter and so on. I think people will like it a lot. We had a nice chat, but now it's getting we're at one. I wanted to keep it 1 hour because I realized that
Aggressively use the edit button and you'll be fine.
for sure. Thanks a lot, both of you, for joining. And
It's my pleasure.
And Peter, let's in October maybe we could talk about something related with Halloween. I don't know. Because we went to the story of ray tracing with all these other discussion. Maybe next time we could go like the story of horror movies or whatever. I don't know. I'm just speaking shit out of my head right now. Anyways, thanks a lot for joining, Olivier. Thanks a lot for joining, Peter. And once again, the show is going to be available, and if you're listening to it right now, it's on Spotify, Google, iTunes, YouTube, whatever you want. Pharmacie Jean Coutu, which is it's okay, that's a Quebec joke in here anyways, because there's sorry, I'm getting a real tired right here. So yeah,